Good morning, everyone. Today, we'll be talking about functions, and we'll try to do it in the simplest way possible. I'm sure you have your textbooks and plenty of online resources available, including mine. However, I'd like to try to help you understand the concept of functions better with lots of examples. First of all, let's ask ourselves if functions have synonyms. Yes, functions can also be called applications or maps. Then, how do we indicate a function? We can use any letter of the alphabet. Perhaps F, to remind us that we're talking about a function by using its initial. Alternatively, we can use letters like A, B, G, H, or even Greek letters like alpha, beta, gamma, and so on. So, how does a function work? What are the main ingredients of a function? They are definitely sets, which we'll denote with uppercase X and Y, assuming they are non-empty. Before we even understand how a function application or map works, we can start writing the rule. We'll write f, x-y to indicate that this function starts from a starting set, which we'll call the domain and is denoted by set x. It ends in the target set, which we'll call the codomain, denoted by set y. We can think of a function as a kind of rule or law. What does this rule do? This rule takes any element from the domain, which we can call lowercase letters x, and for the sake of clarity, we'll use x to represent elements of the set x. For each element of this domain, the function associates one and only one element from the codomain, which we'll call lowercase y and denote it as belonging to the set y. This is a first definition that we find everywhere in all the notes, but there's also a mathematical expression that uses precise symbols to abbreviate what we've written in words. In fact, we could equivalently say that the function f from x to y is a law that, for every element x in the domain x associates, or maps, or there exists one and only one element y in the codomain y. So, we could write the universal quantifier for every x in the domain x, which belongs to x, there exists, and here we'll use the existential quantifier, so it's there exists, indicated by the upside down e, and to indicate that the element must be unique, we'll use the exclamation point. So far, nothing new, as we've only given the definition of a function. But we still don't know how to distinguish it, recognize it, or at least create it. We can also invent a rule that serves as a function. So, how can we do that? In reality, the first thing we can do is invent two sets, establish these sets today, make them the elements that belong to these sets, or we can use numerical sets like the set of natural numbers, integers, rationals, or even subsets. In this example, I want us to have precise sets whose elements I'll put in set X, I'll put the first 3 letters of the alphabet, and in set Y or the codomain, I'll put the first 5 natural numbers. As you can see, I've represented this with a curved arrow and labeled f underneath it to remind us that we're representing a function, which I'll call function s. The fact that I've drawn this curved arrow gives me the idea that this function is a kind of bridge. I'm taking all the elements from set X and making them cross this bridge, and in the process of crossing the bridge, they transform into the elements of set Y. This is something you probably shouldn't mention during an exam or when explaining to your teacher because they might not appreciate it. Remember, this lesson aims to simplify the concept of functions and speaks in a slightly more informal manner. Later, I encourage you to revisit the definition we discussed earlier, which is a middle ground between informality and formality. Now, as you can see, I'm starting to draw red arrows to indicate that I have elements in set X. For example, I'll start with A. I want to associate the number 5 with A. So, what do? I draw an arrow starting from A and ending at the point 5. I do the same for B, which goes to 1, and for C, which goes to 3. Of course, I've chosen these values randomly, I've drawn arrows randomly. I could have chosen to associate 2 with A and 3 with B, and 4 with C, and 1 with A. Anyway, you get the idea. This is an example of a function because I followed the definition. Function f is a rule that takes any element in set X and associates one and only one element in set Y to it. Now, I wonder if I can express what I've just represented mathematically. In the diagram, I represented A and said that I'm associating 5 with A. But how can I write this mathematically? Can I write f A equals 5 directly? F A means the image of A through the function f, i.e., the image of A through the function is 5. The term image refers to the element in the codomain Y that corresponds to the element A in the domain X, so, as you can see, we've represented the elements of Y earlier, that letter Y, and now we've found an alternative way to represent the element by using the element from the domain X to which 5 corresponds. Remember that when we write the elements of the codomain as images, it means those elements correspond to some elements in set X. If we want, we can also write f B equals 1 to indicate the image of B through F, which is 1. And f C equals 3 to indicate that I've associated the number 3 with A. There are other ways to represent the function while considering the same sets X and Y, which are the domain and codomain. Certainly. However, now we're in a particular situation. Let's make it so that the elements A, B, C in set X correspond to one and only one element in set Y. And interestingly, this element is the same, both A and B correspond to the number 5. Now, a spontaneous doubt arises. We wonder if the rule we've invented is worthy of being called a function. So, how can we determine if what we've represented is actually a function? Let's refer back to the definition of a function itself. We've said that a function is a law that takes all the elements in the domain and associates one and only one element in the codomain. As you can see, these are the only pieces of information we have at our disposal. There's no mention of an element in the codomain that can't be the image of multiple elements in the domain. Indeed, this is possible. What we've represented could still be a valid representation of a function. It could happen that the three elements A, B, and C can even correspond to the same element. There are functions where the codomain consists of just a single element. In such cases, when we make all elements in the domain correspond to that one element in the codomain, we've still created a function. Returning to the previous exercise for completeness, let's write down the elements we've taken from the codomain as images of elements from the domain using the function. So, we'll write f A equals 5, but also f B equals 5 because both elements A and B have the same image. Whereas f C equals 3 because C corresponds to 3. And if we wanted to provide an example of a non-function, all we need to do is take an element from the domain. At least one that has different images. For instance, A could be made to correspond simultaneously to both the number 1 and the number 5 in the codomain. This is an example of a non-function because, according to the definition, we can only associate one and only one element from the codomain with each element from the domain. Another example of a non-function is one that doesn't consider all the elements of the domain. Perhaps it only takes some elements from the domain and correctly associates elements in the codomain, but it doesn't do this for all elements in the set X. Now, let's consider if we can build a function with infinite sets. Well, yes, we can consider sets X and Y as infinite sets. We could even set them equal to numerical sets, such as the set of natural numbers, integers, rationals, reals, complex numbers, or even finite and infinite subsets of the sets I just mentioned. If at least one of the two sets, the domain or the codomain of the function, is infinite, then we set aside the representation using Euler's diagram, meaning the drawing, and directly write the function indicating the domain, codomain, and explicitly stating the rule. In this case, we indicate the equation, and then we assign, using an arrow that starts with a vertical segment, a specific element of the codomain. In this case, it's y equals f, x plus 1. In fact, we've taken a function, with the domain being all the real numbers and the codomain also being all the real numbers. And for each element of the domain, which we'll call x, we assign the element of the codomain y equal to x plus 1. We're considering a function that assigns to every real number its successor. Although we can't represent this graphically using Euler's diagram, since we're dealing with infinite sets for both the domain and codomain, we can proceed by simply writing the function, indicating the domain and codomain, and explicitly representing the rule. We indicate the equation y equals f, x plus 1, and this represents the function that assigns each real number to its successor. Of course, the number of functions is infinite due to the fact that the domain and codomain can be infinite sets. Throughout your studies, you'll encounter numerous functions. You'll learn to distinguish between a function and its graph. I look forward to the next lesson where we'll delve deeper into functions and explore injective, subjective, and objective functions along with much more. So, I'll see you then.